at section 10.8. All right, section 10.8. Sorry about that. I started too quickly. All right, allowable stresses, factors, safety, or safety factor. Same thing. Safety factor is easy to abbreviate as SF. Okay, remember I said that my nomenclature forever is going to be that sigma means the actual axial stress, okay, or tau would be my actual shear stress. Okay, no subscript means actual. If I want to talk about the allowable, I'll do sigma A for allowable stress. Okay, or tau A for allowable. All right, so talk about what allowable stress is. That's the most stress that a material can withstand and still be considered safe. Okay, under the loading conditions that you're applying, the forces that are acting on it. Now, allowable stress is also referred to as design stress. Okay, that's the amount of stress that we are designing it for. We're saying, hey, this is what we're planning, or also known as working stress. Okay, so this is how much we say it should be handling, not how much it takes to fail this thing. We're saying this is how much you should be working or using it as, or this is what we're designing it for so that we know it's going to be plenty safe. Okay, so with axial or normal stress, if we say, we know sigma is equal to F over A. So if we say we know the allowable, we're going to say, here's what you're allowed to have, the amount of stress. Okay, well, we've still got F over A. So if we say we know how much force we're going to put on it, and we know how much stress it's allowed to have, okay, if that's known, then this area that we're going to calculate is the required area. Okay, that's the minimum area we have to keep the stress at that level. Now, if we said, okay, well, hey, here, our allowable stress is this much. If we say, okay, we know the area of it, then what that's going to allow us to do is we can calculate what the maximum force that amount of area can handle and stay within that allowable stress. Okay, that's the maximum force. We can always go lower. Having stresses in your components lower than the allowable is fine. Higher than the allowable, bad juju. Okay, and it's the same kind of thing for the shear stress. Okay, if you know what the allowable shear stress is, you know the amount of force, then you can figure out what your required or minimum area is going to be. And if you know the allowable shear stress and you know how big the object is, then you can figure out what's the maximum amount of force you can put on it in shear. So let's talk about factor safety or safety factor. I know in the book it says F.S. I learned safety factor, so I write S.F. They are equivalent. All right, so talking about the safety factor. If we want to talk about safety factor and we want to talk about in terms of the loads, okay, forces, then we'd say that the allowable amount of force it can take, which is what's up top, divided by the actual amount of force we're applying, gives us our factor of safety. So if we say, okay, hey, this material, we can withstand a load of 100 pounds, but we're only actually applying 50 pounds. We get a factor of safety or safety factor of 2, which means it can hold twice as much weight as what we're actually putting on it. And then if you want to talk about its safety factor in terms of stresses, okay, in this case axial stress, I'm using sigma, it's the same kind of deal. The allowable axial stress divided by the actual, what we really got, stress, gives us our safety factor. So if we're allowed to go up to 100 psi before it's not safe, but we're only actually applying 20 psi, we've got a factor of safety of 5. It can take 5 times what we're putting on it. Okay. Now you got to keep in mind in the book it shows equation 1010 and it says factor safety is the ultimate divided by the what's that actual. So here's the deal. You've got brittle material and ductile material. Ductile material is somewhat flexible. It'll yield, it'll stretch, it'll bend. Brittle materials, they won't yield. They're just going to fail. Okay, they're going to snap. So based on the type of material, ductile versus brittle, that determines what stress you use because you've got what's called yield stress, sigma y, where the material stretches or bends and it's permanently deformed. It's never going back to the way it was. But you also have what's called the ultimate stress, sigma u, and that's the most amount of stress it can take, period. And if a material, which is ductile, it yields and then the atoms rearrange, it can take more load and it goes up to an ultimate and then it starts going down and before it breaks, the amount of load it can take. With brittle, it doesn't yield, it just goes up and up and up until it gets to the most it can take and it snaps. So when you're calculating a safety factor, you need to look at what type of material it is. If it's ductile, okay, then you want to use your safety factor is equal to the yield stress divided by the actual stress, what you've got. But if you've got a brittle material, since it doesn't yield, you got to go with the one that's close, that's at failure. The safety factor is equal to the ultimate stress divided by the actual stress. Okay, with ductile, it's nice. It's going to yield before it gets to the most amount of stress it can take before then it later breaks. So you want to go with the safer option. So ductile materials have that safer option to yield. Brittle materials don't yield, so we only have one choice, the ultimate. Okay, so let's take a look. If you look in the book, there's a nice example. I highly recommend it. Example 1010 already worked out for you. Take a look at it. Very good. So let me do some problems at the end of the section for you. All right, let's take a look. Oh, and like I mentioned, example 1010, great real world example. It's got multiple parts to it. You got to look at different things going on, different places where it could fail. So really, take a look through 1010. Great, great problem. Okay. 1032, it says a circular bar supports an axial force of 35 kilonewtons. If the compressive stress in the bar is not to exceed 75.8 meganewtons per meter squared, determine the diameter of the bar. Okay, so they told us they're giving us the amount of compressive stress it can take. So my picture showing the 35 kilonewton force in compression is right. All right, so I want to find D, my diameter that I've listed. So 2, look at my diagram, you'll see the information, and they've told us that the compressive stress allowable, so compressive stress is axial, so sigma C comma A for allowable, is equal to 75.8 megapascals. Okay, we can't go above that and be safe. We're assuming that is a short bar, okay, because if it's a short bar, then sigma compressive is just equal to that axial force divided by the area. So this is really easy. They've told us what the allowable is. So sigma compressive allowable is equal to, well, we know how much force we've got, so that means we can figure out the required area, how much area we have to not go over that amount of stress. So they told us the allowable stress is 75.8 megapascals. That's equal to the force 35 kilonewtons over the required area. Well, it's circular, so the area is pi times d squared over 4. Great. The only unknown is d, the diameter. So if I rearrange this equation, okay, if I bring the d squared up and bring the 78.5 megapascals down, I get d squared is equal to 35 kilonewtons over pi times 75.8 megapascals, whole thing over 4. Okay, you know that basically that pi 75.8 over 4 is the same as dividing by that is the same as multiplying by the reciprocal, so the 4 comes up, multiplies by the 37 kilonewtons. Now, I've got kilonewtons up top, megapascals down below, and I need to make sure that my units work out. So I've either got to convert the 35 kilonewtons into meganewtons or the megapascals into kilopascals. Doesn't matter which way you do it. Okay, so this goes to, and let's see, maybe it's easier to go mega to kilo because it's just another 10 to the third. So 35 kilonewtons over pi times 75.8 times 10 to the third kilopascals. Okay. And then since it's divided by 4, it's the same as bringing the 4 up to the top and multiplying. Okay, so a pascal, you'll remember, is a Newton per meter squared. So a kilopascal is 10 to the third pascals. So this kilopascal becomes 10 to the third Pascal, newtons per meter squared. That's not what I want to do. What do I want to do? Oh, silly me. Kilopascal is just a kilonewton per meter squared. Okay, so kilonewtons up high, kilonewtons down low. Since the meter squared is in the denominator of the denominator, it comes up high. So we get that if you then take the square root of that, okay, so we'll have meters squared, we square root it, and we get meters, which is a distance, a length, which is what we expect for the diameter. So the minimum diameter is equal to 0.02425 meters, okay? I only need 3 sig figs, and 0.02 meters doesn't really mean a lot to most people. So 1 meter is 1,000 millimeters. Meters up high, meters down low. See, this is why I'm talking about you got to make sure that your units work out. And we get 4.3 millimeters. Okay, so that is the minimum diameter required to keep our stress at 75.8 megapascals. If we make the diameter bigger, we get a bigger surface area, so our stress will drop down because force per unit area. Okay, so minimum diameter is equal to 24.3 millimeters. All right, problem 1035. It says a steel column shown, and they've drawn a picture in the book, which I've drawn in my here, supports an axial compressive load of 10.5 kips. Notice, even though that steel column is hollow, the force P still acts at its centroid, which is at the center of the pipe. Okay, so you've got an P is equal to 105 kips. So write that in diagram. Okay. The allowable compressive stress in steel is 20.5 KSI, and the allowable bearing stress in the concrete footing is 700 PSI. So for part A, we want to determine the required cross-sectional area of the column so that we don't exceed the compressive stress of steel. Part B, if the column is made of standard weight steel pipe, what's the smallest nominal diameter that can be used? Nominal means in name only. Kind of like a 2x4 piece of wood is not 2 inches by 4 inches, it's 1.5 by 3.5. Okay, so you're going to we'll look in a chart, and based on the cross-sectional area we need in part A, we will pick the right size pipe, actual pipe. For part C, based on the nominal size of pipe that we picked in part B, we're going to compute what the actual stress in that column is. And for part D, calculate the required length of the steel plate if the width of the plate is 10. Okay, so what we've got to be concerned with here is we're going to have, because we've got P going down, the pipe is in compression, so we've got to make sure we don't exceed its compressive allowable stress. And then this whole thing is trying to squish the concrete, so we've got bearing stress there. Okay, so step 2, my diagram is there. All right, we know that P is 105 kips. Now, they told us that the allowable stress in the steel column, compressive, is 20.5 KSI for the column. Okay, they told us that the allowable bearing stress, so sigma B allowable for the concrete, is 700 PSI. Sorry, for the concrete. What else? We're assuming that this is a short column, so that buckling is not an issue. So we use sigma compressive as P over A. Now, we're neglecting the weight of the plate. Plate weight. We're assuming everything's rigid. Okay, we're not going to get any deflection, deformation. Now, we're going to have to use a table in the back of the book to find some information about our materials. So the table on page 474. So step 3. All right, the equations that we're going to need. Well, we got to find compressive stress. So sigma C allowable is equal to the force we've got, P, over the required area, how much we need. Okay, and we know that bearing stress is equal to the force P that we've got over the area of contact. Okay, so let's go ahead and start solving this thing out. Part A, the required area of the column. Okay, well, we know the allowable compressive stress in the column. They told us that that's 20.5 KSI. That's equal to the amount of axial force we have, which is 105 kips, over required area. So we just cross multiply and we get the required area is equal to 105 kips over 20.5 kips, KSI. Now KSI, remember, is a kip per square inch. So kip over kip, the inches squared comes up, and therefore the required area is equal to 5.12, and we get square inches are our unit, so good. Area, squared inches, I feel good. I'm getting the right unit, so I'm feeling pretty confident. Let's take a look at part B, the smallest nominal diameter if we make this thing out of standard weight steel pipe. Okay, so looking at the table on page 474. So flip back in your book while I write this. Okay. So let me look at my table on page 474. 474. All right, there we go. It's pipe dimensions and properties in U.S. customary units. Okay. Now we found out that our pipe, the column, has to have an area of 5.12 inches squared. That's the required or minimum area. So when I look at them, on this table, I want to look at the first, second, third, fourth, fifth, sixth column, what the actual area is in square inches. We need at least 5.12. So I start moving down it. Okay, 4.3 is still not big enough. 5.58. That's more than we need. There is no one that's 5.12. So we need that or bigger. So 5.58 square inches, if I slide to the left, we see that the nominal diameter is 6 inches. There you go. There is part B done. Okay. Remember, our area's got to be what we calculated or more. Okay. 5.58 inches squared. Okay. So part C. They said find out what's the actual stress in the column based on that pipe we chose. Okay. So actual compressive stress is equal to the force we've got, 105 kips, over the area we've got. Well, the actual area of this 6-inch nominal pipe is 5.58 inches squared. Okay, we've got more area than we actually need, so our stress is going to go below that allowable. Okay, so we've got kips per square inch, so we get KSI, and it's 18.82 because we begins with a 1. KSI. That's our actual stress. It's good. Got to be, because we're allowed to go up to 20 and a half. We're below that, so great. We know we're in good shape. For part D, they said, all right, what's the required length of the base plate if the width is 10 inches? So let's take a look. That base plate, here's my base plate. I'll draw a pictorial. They said, what's the length? So here you go, length. If the width is 10 inches. Now, that plate, we've got the amount of force P on the column is transferring, if we neglect the weight of the column, which we did, right? Part 2, neglecting the plate weight, and the column weight. Okay? Then the only force on this plate is going to be P. Okay? Now, the area of contact between that and the concrete, we're worried about it, we're going to crush the concrete, area of contact is going to be where the plate touches the concrete. So we're talking about bearing stress, and our bearing stress allowable is 700 psi, and we know that bearing stress is equal to the force you've got, axial force, over the area of contact. So our area is just length times the 10 inches. So 700 psi, pounds per square inch, is equal to 105 kips over the length times 10 inches. So cross multiply, and I get the length is equal to 105 kips over 700 pounds per square inch times 10 inches. Okay, inch over inch squared just leaves me with inch. Now kip, I can't have kips up top and pounds down below, so I'm going to have to convert one. It's going to be easier to convert a kip or kilopound into pounds. It's just 105 times 10 to the third pounds over 700 pounds times 10, and we get inch. I'm canceling out the inch over the inches squared. All right, so now pounds over pounds cancel out, so the inch comes to the top, and therefore not that, looking above, we're not thinking. The minimum length I've got to have to keep our bearing stress under that 700 psi is 15.00 inches. Okay, so I end up with units in inches, which is good because that's the units for length. So then part 5, I would just write in the answer. And there you go. Step 5. All right, let's take a look at problem 1038. Here's a good one. If you look at it, look at the picture in the book. It's going to take too long to draw it out here. Two 3/8 inch thick by 6 inch wide plates are joined by 3/4 inch diameter rivets as shown. Okay, there's two of them. Determine the maximum allowable load P on the plates if the allowable stress in tension is 22 kSI, the allowable stress in shear is 29 kSI, and the allowable stress in bearing is 58 kSI. Okay, so we've got three ways that this thing could fail. We could fail it by stretching the plate too much axial stress on the plate. We could fail this thing by shearing the rivet, okay, making it snap on a plane that is parallel to its cross-sectional area, or we could fail this thing by crushing, okay, where the rivets and the plate meet. So we've got a limiting factor on each. So we have to take a look at each, find out that if it was to fail, if the plate was just to fail in axial stress, how much load could we apply? Then we look at it and say, okay, if we were to shear, how much force P does it take to shear the rivets? And then also how much force is caused to make this thing to crush the rivets or that edge of the plate. And then whichever one is the lowest amount of force, that's the one we have to design for. Okay, so let's take a look. Step 2. The diagram that I'm not drawing right here. Well, I'll draw a couple of little pictures as we go. Okay, we're neglecting the weights of the plates, the rivets. Okay, we're assuming that they're rigid. Now, these plates are in tension, so we don't have to assume they're short, because that's only for compression. Excuse me. All right, so step 3, we're concerned about it shearing. Shearing, yes. So tau is equal to the force in shear over the area, shear area. We're concerned about failing to see in tension, making the plate break. So sigma is equal to the force that's axial over the cross-sectional area. And in bearing, we're concerned with the axial force over the area of contact. Okay, and if you remember, for a pin, a rivet, a bolt, the area of contact is the projected area, which is equal to the diameter of the fastener times the thickness of the plate. All right, so let's go ahead and start cranking it out. Step 4. All right, so first let's look at the plate. Is it going to fail in tension? Are we going to have too much tensile stress on this thing so that it might stretch or break? So when we're looking at the plate, say, all right, sigma allowable, the allowable axial stress, we can figure out we've got a known area. We can't change the size of the plate, the thickness or the width. So we know the area, so we can figure out what the maximum amount of force P to put on this thing is. Okay, and our area is going to be equal to, well, the plate. If I'm looking at my plate, and this thing is in tension, P applied at the centroid. Okay, the area that is normal to the axial force is that area. Okay, so the area is just the width of the plate, 6 inches, times the thickness of the plate, which is 3/8. Okay, so that's equal to 2.25 square inches. So let's fill in the known values. The allowable stress in tension is 22 kSI, and that's equal to the maximum P, and let's say maximum P sub T for tension, because if we're going to fail in tension, this is how much force we can apply, over that 2.25 square inches, And so, therefore, we get 49 P max in tension is 49.5 kips. Because KSI, kips per square inch times square inch canceled, and I'm left with kips. Okay. So that's the most force we can apply on this plate and not fail the plate in tension. That's why it's comma T. Let me make sure that's comma T. Okay. Well, now let's take a look at the rivets. Let's look about shearing those rivets. Okay. We know that the allowable shear stress, we know the area, well, we can calculate the area of shear planes. That's a given. We know the size of the pins. That's not a variable. So we're going to be able to get from this the maximum shearing force based on this equation. Okay. Now, if we take a look at, here you go. And I'm going to draw them without their heads. There's my two pins. There's the plate. Okay, that we're applying the force P to. So, because I've got one plate up high and one plate down low, with the pins going through them, okay, the place where sliding is going to occur is here, okay, on that plane, that surface. Now, the issue is we've got two pins. So our shear area is the combined area of those two pins. Okay, so our shear area is equal to the area of both pins. So the area of one pin is pi times the diameter of the pin, which the diameter of the pin is 3/4 inch, 0.75 inch, pi d squared over 4, but we've got two of them. So I've got to take that and multiply it by 2. 2 pins. Okay. So what we get is we get an area, our shear area is equal to 0.884 square inches. So now we know what our shear area is. They gave us the allowable shear stress, so we can calculate what the maximum force in shear is going to be. Now, what force is causing these to shear? It's the force P. So our tau allowable, 29 KSI, is equal to that force P max in shear divided by the area, 0.884 inches squared. So we get that P max in shear, to shear it, is 29 KSI, which is kips per square inch, times 0.884 inches squared. This time I'm actually showing you inch squared up high and squared down low, so I get kips. So get rid of that and write it down here. It just stands out. Therefore, the maximum force I can apply, P, and before I shear these pins, is equal to 25.6 kips. All right, well, now let's look at this thing at bearing. Okay, so let's make sure that we're not going to crush anything. Sigma bearing allowable is equal to the projected area, okay, and whatever that maximum P is in bearing, okay, stress divided by the projected area since it's a pin. In this case, our projected area Okay, now let me show. Here's our, it's kind of like the example I showed just a little bit ago. Like that. Okay, remember our projected area is just that, but we've got two of them. So our projected area is the diameter. Oops, write it numbers. Diameter of the hole of the pin, 3/4 inch, times the thickness of the plate. But we've got times 2, because we've got two projected areas. Okay, they're both sharing. Those two projected areas are sharing that force that's causing a bearing stress. So the allowable bearing stress is 58 KSI, and that's equal to P max sub comma B, the maximum force that we can apply and not fail this thing in bearing, divided by the projected area, which is 0.563 inches squared. So we get the maximum amount of force P we can apply to not fail this thing in bearing is 32.7 kips. Okay, well, we've got three values of P. Okay, to fail in tension, the plate in tension, we'd need 49.5 kips. To fail the rivet in shear, we would need 25.6 kips. Okay, both P. Remember, that's the force P applied to the plate. And to fail this thing in bearing, it would take 32.7 kips. So we look at all three of those and we say, well, hang on. If I apply 49.5 kips, well, that's more than 25.6. So I would have sheared those pins, and it's also more than bearing, so I would have crushed something. Okay, now obviously it would have sheared first because that's the lowest one. So what we want to do, if we want to make sure it's not going to fail in tension, shear, or bearing, what we do is we compare those three values. P max in tension, P max in shear, and P max in bearing, and use the lowest value. Because whichever way it's weakest, if it's not going to fail there, it's definitely not going to fail in the other two ways. So, step 5, P max, maximum amount of force P we can pull with those plates and not fail it in any of the three ways, is 25.6 kips. In part 2 of this section's videos, I'll do problems 1039, 41, and 44.